So the phenol is a benzene with a hydroxyl group on its crazy stuff, right? But what we're gonna focus on specifically for the phenols, we must describe the reactions of phenols with acyl halides, right? Aqueous bromine and sodium hydroxide. We must describe the formation of the azo compounds and the coupling reactions, and we must state the uses of azo compounds. Them something we're gonna focus on. All right, just bear with me, you know. Do you guys need a no? You guys can't have a break. We only have 10 minutes. All right. I'm not. Do you guys are you guys willing to go over a little bit just to complete this? Let me see how many slides are left. Oh, we don't have many slides left. So you guys just want to complete this? Okay, I'll just complete.
Yes, sir.
Yes, sir.
Yes, sir. Let's
Yeah, I'll just complete. So let's do an introduction into phenols. Phenol C6H5OH, that is our molecular formula for phenols, right? It has a OH group, a hydroxyl group attached directly to the benzene ring in place of the hydrogen atom. Let me just draw the phenol. All right. Phenol, lovely. Right? Sometimes it was called hydroxybenzene at the time, but we call them phenols now, right? So let's have a look now. Phenol is only sparingly soluble in water. Not that soluble, sparingly soluble in water because of the large aryl group, right? Minimizes hydrogen bonding in with water molecules. So some persons see the OH group and say, all right, this can dissolve in water. Not true. It can sparingly dissolve because it does exhibit some amount of hydrogen bonding because we know how OHs react. So we know hydrogen bonding and all those type of stuff. It can have hydrogen bonding, right? But because of the large aryl group, it tends not to dissolve as best as possible, right? The hydroxyl group doesn't always react in the same way as an OH group would react in alcohols. So don't assume that they will react in the same way. For example, phenols are acidic, whereas alcohols are not. We're going to look at this now. Alcohols are slightly acidic. Alcohols are not as acidic as phenols, right? The hydroxyl group has an electron donating effect on the ring. So it's the same thing like the methyl group. It's an electron donating effect, right? So it increases the electron density on the ring. So what does it mean? Oxygen has its lone pairs on there, right? So the lone pairs will participate in the ring. So the lone pairs are going to be drawn closer to the ring system and participate in the ring system. So it increases the electron density on the ring, right? And this tends to increase the reactivity, right, of these phenols, right? So it increases the reactivity to electrophiles and to electrophilic substitution. By the way, phenols can turn blue litmus red or pink, right? So it is acidic. The acidity of phenols, we're going to speak about the acidity of phenols when we talk about organic acids and organic bases, right? And then here we see the resonance stabilized structures, right? We have resonance stability for phenols as well. And we also see that when the hydrogen is gone, we have what we call a phenoxide ion. All right? Any questions? We're going to talk about the acidity later when we jump into acidity specifically. All right, let's not confuse ourselves right now. Go ahead. Any questions?
Sir, what's the aryl group again, and why is it called aryl?
The aryl group is our benzene group because it is an arene. Arene is to aryl as methane is to methyl. You get me?
Oh, yes, sir. I think so.
Okay. So arene is to aryl as methane is to methyl. So that's just what we call it, the aryl group. Just like the methyl or ethyl group or the hydroxyl group. Okay? So the aryl group will be a group that displays aromaticity. Right? Lovely. Reactions of our hydroxyl groups in phenols now. The first reaction. Note, we don't need the mechanisms, so we just need to know what's happening. We need to know what's going on. So the reactions with alkali. Alcohols do not react with sodium hydroxides. However, due to the acidic character of the phenol, it does. So remember what we said earlier now. Not because it has a hydroxyl group means that it undergoes the same reactions as alcohols. It doesn't. Right? It's different. So whereas alcohols don't react with sodium hydroxide, phenols do, right? Because phenols are organic acids. Therefore, An acid and an alkali would react to give us a salt and water. Right? So what we have is sodium phenoxide and we have water. No, no, no. Let me make this clear, abundantly clear. If I ever see this, just pack your bags and go home. What is wrong with this that I've drawn?
It is implying a covalent bond between the O and H, but that's not so.
Between the O and the Na, all right, the sodium, all right. So that is not true. Lovely, thanks for that, right? It is an ionic interaction. It is a salt. So keep it like this. Never draw a bond because what if you draw the bond? What you're telling the Cape examiner is that this person passed Cape chemistry in one and C-sec chemistry, and telling me that a metal and a non-metal have covalent bonding, right? That is what it's telling them, right? So if I was an examiner, me fail you long time, no matter of the content of the rest of the paper, because that means I don't know chemistry. Alright? But actually we metals and non-metals can create covalent bonds, but that's at higher levels chemistry. Right? At Cape we say that they don't. So let's just keep it like this for now, right? In this reaction,
Wait,
right?
sir, you could like fail a whole paper if
No, no,
made
no, no,
like
no,
one big
no.
mistake.
I'm exaggerating. You won't fail the entire paper. You'll just get that wrong.
Oh, good.
No, I'm insinuating that you should probably fail the entire paper. But people make mistakes, so you can't actually fail the entire paper. But if you brave, big, bad, and bold, and put a covalent bond between these two, something must wrong. Right? So just remember to always keep it ionic. Keep it ionic. Okay? So the second reaction is reaction with sodium itself. Not sodium hydroxide, but sodium itself. We have the creation of phenoxide, but then we have the creation of a hydrogen. Because you know why? Do you know why? Do you guys know why? Because a phenol is an acid, and an acid and a metal gives us salt and hydrogen gas. Simple. These are things that we've been seeing for centuries now. An acid and a base gives us salt and water. An acid and a metal gives us salt and hydrogen gas. Everybody's fine with that? Everybody's fine?
Yes, sir.
Alright. Here now, we have the reaction of phenol with bromine. So bromine water, aqueous bromine reacts rapidly with phenol to create a white precipitate of 2,4,6 tribromophenol, right? Similar to what we can see in the methyl case, right? So 2,4,6 tribromophenol is created and no halogen carrier is needed. Why is no halogen carrier needed? Why is there no Friedel-Crafts reagent needed? Anybody? Why is it not necessary?
The
Go ahead.
OH, the OH make the benzene, well, the pi system in the something them more reactive.
All right, because the free electrons on the hydroxyl group can be donated to the ring as the hydroxyl group is an electron donating ring, increasing electron density on the ring, right? Increasing its likelihood for electrophilic attack. Lovely, right? And we had a rapid creation of 2,4,6 tribromophenol, which is a white precipitate. Sometimes it shows up as kind of like brownish, but that's probably because they have impurities. Um, so white precipitate, lovely. Go ahead.
Sir, can you explain why the halogen carrier isn't needed again?
Okay, zoom in straight back to the reaction of benzene. Alright, let's go, let's go, let's go. Benzene, right, is an extremely stable molecule. Right? So what we're gonna talk about it in basicity, right, and acidity. But let's look at this, right? We know that the ring itself, the ring system itself, exists in a type of way in which electrons constantly move, right? Following?
Yes, sir.
Electrons constantly move across the molecule, right? This decreases the availability of electrons to be donated to electrophiles. So an electrophile will come in, and an electrophile would want to get electrons, but by the time the electrons, that it focuses itself on, right, is in range, the electrons will move. So electrons constantly move, making it harder for electrophiles to actually get those electrons. So because of resonance stability, resonance means that electrons are constantly moving in a ring system, So it decreases the availability of electrons. If electrons were focused on one area, then yes, we could say that electrophile can ease the attack. In case of alkenes, because in alkenes there's no stabilization, The electrons are there and it's ready for attack. Let me draw the thing right? But within ring systems, the electrons are constantly moving and it's not always available for electrophiles to attack. Therefore, we need to create a really strong electrophile using a Friedkraft reagent. That's good.
Yes, sir. I think so.
If you have a question, you can ask me after, right? No problem at all. That is what I'm here for. Alright, so if you have a question, just ask me. Alright, so let's get into it now. Talking about tribromophenols. Alright, we saw that. Okay, so that is it now, That is it. So you know what this is all preparing us for now? It's all preparing us for azo compound. So these are the reactions of phenols that you need to know. Reaction with alkyl, with sodium, and the reaction with bromine. That's all you need to know. Alright? So we looked at the reactions of benzene, we looked at the reactions of methylbenzene, we looked at the reactions of nitrobenzene, we looked at the reactions of phenol. Now let's look at azo compounds. Azo compounds are dyes, right? Has anybody used methyl orange as an indicator within titrations before? Methyl orange is an azo compound, right? So let's have a look at this. Diazotization is our first reaction we must look at. Diazotization, right? It is important to note these things about diazotization. It's the reaction of aromatic amines, right? Aromatic amines and phenols, right? It must be in the presence of nitrous acid rather, right? Hydrochloric acid, right? And must have some salt present, right? So usually we can use a sodium nitrate or use like a sodium chloride, right? Sometimes we can use that to increase the chloride concentration, right? Using the common ion effect. We do that already in a unit one. I'm not going over that. And it must be done at glacial temperatures as well, around below 10 degrees Celsius thereabouts, right? So phenylamine, an aromatic amine, reacts with nitrous acid in the presence of hydrochloric acid to form a diazonium salt, right? So this process is called diazotization. So phenylamine in the presence of nitrous acid. Notice it's not nitric acid, acid is for the nitration. Nitric acid is NO3. But in this case we have NO2. This is nitrous acid. Alright. So nitrous acid and we have our hydrochloric acid at glacial temperatures below 10 degrees Celsius and we end up getting benzene diazonium chloride. Benzene diazonium chloride. Nitrous acid is unstable and so is made by adding sodium nitrate and hydrochloric acid. So that is how we create our electrophile, right? And we add that to the phenylamine to create our diazonium salt. Hoping we can see that now. Hoping we can see that. Okay. So the phenylamine will react with the nitro group and actually create a triple bond. So let me draw it out a little bit more, right? So we end up with something like this, with a positive bond charge there and a chloride interaction there. And this is our diazonium salt. Why is it diazonium? Because azo refers to nitrogen. Did you guys know that? Azo refers to nitrogen.
Nope.
For nitrogenous compounds. I'm slowing down a bit so you guys can catch up. right? It's derived from the Latin word for nitrogenous compounds, right? So use azo. That is our prefix for nitrogenous compounds. So it's diazo because we have two nitrogens. So it's a diazonium compound, right? So this is a diazotization. What is diazotization? Right? Diazotization requires a phenylamine, right, reacting with nitrous acid in the presence of hydrogen chloride or hydrochloric acid to give us a diazonium salt and water. Make sense? Does it make sense? Guys, does it make sense? Questions? Are there any questions? Let me check the chat real quick. So where's the chloride? Oh, the chloride is attached to the nitrogen there. Right, so the nitrogen has a positive charge, so the chloride has a ionic interaction there. Alright? So the chloride is attached like that. You can see that there. Okay? Okay. That is it. Okay. Coupling reaction is our last reaction we have to look at now. The benzene diazonium chloride reacts with an alkaline solution of phenol to form an orange dye, 4-hydroxyphenolazobenzene, or what we call p-hydroxyazobenzene, right? So note, the benzene diazonium chloride will react in an alkaline solution of phenols, right? And then what we end up with now is 4-hydroxyphenolazobenzene. This is called the coupling reaction. Go ahead.
Sir, how do we get an alkaline solution of phenol if phenol is acidic?
Okay, so we're going to add sodium hydroxide to increase. We're talking about the alkaline solution of phenol now, right? So we have the phenols and we add a base to increase hydroxide concentration. That is what we do. Thanks for that question. It was lovely.
Okay, sir.
All right. And the temperature must be glacial as well. All of this is happening at glacial temperatures now. All of this is happening below 10 degrees Celsius now. Because it will break apart if it's not done at a low temperature. The positive charge of the diazonium ion acts as an electrophile and it substitutes into the fourth position of the ring of the phenol. So I could understand what's happening here because I want you guys to see it. Don't want you guys to be some of those students who say, all right, that is what produced. Right? And then you go on an exam paper and them ask if you tell us, show us a little mechanism or show us where it connects. And then everybody lost. Um, so let me get a slide, an empty slide, and let's look at the coupling reaction. Can you guys still see my screen?
Yes, sir.
All right. Can you still see my screen now?
Yes, sir.
All right. So we start out with alanine, or what we call phenylalanine, right? Well, not phenylalanine. That's crazy. Phenylamine. Phenylalanine is actually a nitrogenous base, right? That's biological. But we're looking at phenylamine, right? All right. So we start off with that. Okay. What we're going to be doing, how do we do the diazotization? We said for diazotization, we're going to need the presence of nitrous acid, HNO2, plus HCl. And what we're going to be getting is something like this. I'm going to turn it sideways so I can actually draw it properly, right? We're going to end up with something like this, with the chloride ions like this, plus around 2 molecules of water there, right? So we have this now. This is the diazonium ion. All right. After that, now, let me take that apart now. After we have the diazonium ion now, we're going to end up with something like this. Let me turn it sideways because it only makes sense if I turn it sideways. All right. We're going to have the ion specifically. So let's have a look at this. Somebody's on mute. All right. So let's have look at something like this. So we have something like this, right? Phenol, you know. All right. We're reacting with phenol now. So let me just note something. Sometimes we see the chloride group added on different nitrogens, by the way. Right, so sometimes they're found on different nitrogens because they'll bear the positive charge. So whichever nitrogen bears a positive charge, it will be there to negate it. All right. So we're gonna have something like this now. We're gonna have a phenol. Let me turn the phenol this way because this is the way that it's gonna be attacking. We have the OH group here on the phenol, right? What will happen here now, right? Within the presence of the phenol itself, remember, and it's also basic, right? We're going to have an attack, right? A substitution attack. And what that will create is something looking like this. Nitrogen, double bond nitrogen, single bond phenol, right? So we're gonna end up with something like this, OH, and this is our our azo compound. This is p-hydroxyphenol azobenzene, right? That is the name of that compound. Everybody's fine so far? And it is orange. Any questions? Let me check the chat to see if there are any questions. Let me open my phone and look at the chat. Where is it? Why can't I find the chat? Okay. All right. Okay, so everything seems like it's fine. It does take a while to sink in. It does, right? We don't need the mechanism, but I need the mechanism. Um, um, I would recommend that you understand how it works, right? You don't need the mechanism for this, but I would recommend that you understand how it works a little bit, right? Just understanding where the arrows go and those type of stuff, so you can see the creation and what you're creating, right? Because you might be asked to draw the products and stuff like that, right? So hold on now. Phenols, right, have one or more hydroxyl groups attached directly to the benzene ring. You usually look at phenols that have one. The hydroxyl group in phenols react with sodium hydroxide to form a salt and acid halide, uh, right, to form esters. We're going to look at the formation of esters using acid halide because I noticed I didn't have that in the slide. Right, the electrophilic substitution in the ring of phenol is rapid due to the activation of the ring by the hydroxyl group. Phenylamine reacts with nitrous acid below 10 degrees Celsius to form a benzene diazonium chloride. And a coupling reaction occurs when diazonium salts react with phenols to form azodies. Lovely. All right, so that is the recap of the entire thing. All right, I noticed I didn't speak about the acyl halides, right? I know that you guys know what acyl halide is, right? So the reaction that occurs here is basically something like this. It's a um condensation reaction. We have H, we're gonna have the creation of hydrogen chloride, and then the product will just be an ester, right? So it's not anything big. That is the reaction. So we have an acyl halide here, right? Acyl halide reacting with a phenol to produce an ester. Hopefully you guys can see that. Just have a look at it. Don't jump on it too quick. Just have a look at it. All right. So while we're looking at that, are there any questions or concerns? Give me a second. Let me fix.
Sir,
Go ahead.
could you go over the screen that you were showing the mechanism for the formation of the azo salt?
Oh, I didn't save it, you know. All right, let me. Okay, what I'm gonna do? I'm gonna write on this thing, and I'm gonna leave it in the slide. All right. So let me just create a little bit more blank slides, and let's just leave them there. All right. So let me draw this now. Diazonium, right? What we need for diazonium salt production? What do we need?
So we need phenol, we need the diazonium salt, and we need some hydroxide, sodium hydroxide.
We're talking about the formation is a compound.
Yes, sir, that matter.
All right. So let's
You're
draw.
saying that you're
Mm-hmm.
saying we don't have to know the mechanism, but it will be helpful if we do to understand it. So I would like to understand it, so I want to see it.
All right. So let's look at that. All right. So let's just have the chloride there. Um, for the case of this, let me add the chloride here. So the chloride just goes anywhere. It goes on the nitrogen that has a positive charge for you, right? And this must be in the presence of a base. So sodium hydroxide is usually what we use, right? So what tends to happen, right? What tends to happen is that this area is going to attack the fourth position, right, on the phenol. The fourth phenol position. Not seeing anything?
Not sure if it's just me.
Can you guys see the screen? Let me check. Oh my, the screen gone. All right, hold on. Let me see that. Thank you for letting me know. Can you guys see the screen now?
Yes, I can see it now.
All right, lovely. So we have our phenol reacting with our diazonium salt, whatever, right? Our chloride specifically, and then we end up, and then we know that this group is going to be attacking the fourth position on the phenol, right? Where's the fourth position on the phenol? Here, right? One, two, three, four, right? Right? Yes.
Yes, sir.
All right. So we're gonna end up with something like this. So as we said, it's gonna attack our fourth position on the phenol. So we're gonna end up with, I'm not, this is not the product by the way, I'm just gonna show you where it attacks and then I write the product. Boy oh boy, I can't draw to save my life. Um so it's something like this. Let me draw the ring systems. Alright. So one of the bonds are gonna break to attack there, and one of the hydrogens are gonna leave, right? To stabilize the bond. Right? So what we're gonna have. So is that okay? Because I'm gonna erase it now to draw the product. Does this make sense? The person who said that he wanted to understand it, I think it was it Joel?
Yeah, it makes a bit of a sense now, sir. Yeah, thank you.
All right. So that's what's happening, and then we're gonna end up now. Let me erase all these lines. We're gonna end up now with exactly what we had a while ago, right? The attack, right? So the bond broke, So now we only have a double bond between them, and then we have the bond at the phenol, diazonium salt, and it is orange. It's orangish yellow. All right. So yeah. Let me see. Uh-huh. That is the coupling reaction. That's what we call the coupling reaction, by the way. It's coupling reaction, not diazotization. Diazotization is the creation of the salt, specifically the azonium. All right, all right. So we looked at that. Yet another activity. Explain the characteristic difference in the effect of the hydroxyl group. Um, well, when the hydroxyl group is bonded to an alkyl and the benzene ring, respectively. Because what we want to know now, why is it that phenols have hydroxyl groups but they don't react like alcohols? That is what we need to know. So explain the difference, right? Remember, you guys don't have to do it, If you want to do it, you do it and you show me your answer, but you don't have to. Okay? Explain the A with an A down equation what you would see when phenol is added to ethanoyl chloride and an aqueous solution of bromine. Interesting. Ethanoyl chloride is a acyl halide, right? And I looked at the acyl halide briefly in this, right? All this is an esterification reaction. Just like acids and alcohols, carboxylic acid and alcohol, right? Reacts in the same way with phenols and acyl halides. Okay? Same thing. So you should be able to show that. Same thing. No problem. And then another question now. A sequence of two reactions is shown below, right? Give the names of the compounds X and Y, and give the reagents and conditions for reaction 1, and in the type of reaction for reactions 1 and 2. Can you guys answer this? What is X and what is Y? What is X? What is the name of compound X? Should I ask somebody individually? Joel, what is the name of compound X?
Uh,
Nobody wants to? Go ahead, Joel.
okay. Alright, sorry. Isn't it the what do you call that? The diazonium salt. So it's diazonium benzene, diazonium chloride, I think.
Okay, lovely. It is the diazonium salt. And what would be Y? I don't know if Jardine or Nicholas want to tell us what Y is. Victoria or Shanique want to tell us what Y is. Go ahead, Jardina.
There wouldn't it be the azodine?
The azo compound, the azodie. Lovely. Right, the conditions at reaction 1. Somebody else who didn't answer. What is the conditions at reaction 1? Gabriel or Arifa would like to tell me? So if X is the diazonium salt, what is required for this reaction? What are the conditions? We're talking about temperature and we're talking about reagents.
Sir, the temperature would have to be below 10 degrees.
And the reagents.
The reagents are hydrochloric acid and so I don't remember something with sodium.
All right, let's go back. Let's go back. So it's diazotization, yes? So what we need is nitrous acid, hydrochloric acid below 10 degrees Celsius. And where we get the nitrous acid from is sodium nitrate. Nitrate. Yeah, sodium nitrate. Okay? So the information is there. So the answer's there. So the answer's there. Answers for all the questions are in the PowerPoints, by the way. Right? So that is it. Lovely. Lovely try. Now, reaction 2, what are the reagents and conditions? Oh no, he didn't ask for that. What is the name of reaction 2? Somebody else who didn't answer. What is the name of reaction 2? Naila, Nicholas, Ramona, Shanique. Let me check the chat. It's not above, it's below 10 degrees, Ramona. The coupling reaction. Lovely. Miss Walker. Right? That is what the coupling reaction is. And the first one is diazotization. Lovely. And with that, the second topic of the entire syllabus is complete. So really and truly is only one topic we've been doing for an entire month. But all other topics are really, really tiny. Right? So functional group analysis is over, right? With the end of azo compounds. So the next time I see you guys, we will be discussing the the acidity and basicity